everything, and I'll get into that. Some things don't get reabsorbed. So for example, a good, like inulin is good to measure filtration rate. Why? Because it doesn't get reabsorbed or secreted. So basically, it only gets filtered. Whatever gets filtered goes straight to excretion. So think of excretion like exit. Excretion is what you're pissing out, pretty much. So that's why it's a good measure of filtration rate, because you're skipping the whole reabsorption secretion mechanism, right? So with inulin. All right. So yeah, those terms, very important. Reabsorption into the blood, secretion back into the tubule from the blood, excretion is what you piss out. This is a little bit of anatomy, but it's not clear. I'm just gonna go over it real quick. So basically, the fenestrations are actually holes in the capillaries themselves. Has nothing to do with the podocytes or the pedicles. The slits are what's part of the pedicles. All right, so don't get that confused. So the podocyte has the smaller little things, which are the pedicles. Podocytes and pedicles are one structure. It's just the podocyte is the big structure. The pedicles are the little ones. The slits are part of the podocyte pedicle structure. And the fenestrations are the actual capillaries, holes in the capillaries. Huh? Right. So it allows, you know, the stuff to pass through. Same thing. Okay, this graph, I don't want people to get confused with tubules and vessels. This is in reference to the particles in the substance. So this is what this is referring to. So obviously, that membrane is negatively charged. So things that are anionic are going to be very low filterability. Things that are positive are going to be very high, and neutral is going to be obviously in the middle. But this graph refers to the substances in the filtrate. It's not referring to the tubules or the vessels. So that doesn't throw people off. Okay. A lot of people don't know the difference between oncotic and hydrostatic pressure. They just memorize, well, oncotic pushes things in, oncotic pushes things out, whatever. If you know the definition, you understand function. He likes to ask a lot of questions. Well, if this happens, then what happens to this? If you know the definition, then you'll be fine when he tries to throw the questions out there. So this picture is trash. I tried to draw around it, but it's garbage. You understand better with this. So capillary, this could represent the capillary or the Bowman space. As we can see, you know, the Bowman space and the tubule are one in the same space. They're actually the same space. So don't let that throw you off. So hydrostatic pressure, hydrostatic, hydrofluid, it's like blood pressure. It's the pressure that the fluid is exerting on the wall of the arteries. That's what's represented in red. That's pretty easy. The oncotic pressure becomes a little more tricky. When you say oncotic, think of an osmotic, osmosis. Why? Because there's a concentration of albumin in the blood. There's no albumin in the interstitial or in the Bowman space unless you have kidney damage. But normally there's not. So because there's a concentration of albumin in the blood, water wants to move from a place of low solute concentration to a place of high solute concentration. So water naturally wants to, by osmosis, go into the capillary. That's the oncotic pressure. So obviously the hydrostatic pressure and the oncotic pressure work against each other. A balance of those in the capillary and in the Bowman space, because each one has their own, is what gives you your GFR. That's what that equation means. He just kind of slapped it up there and expected you to figure it out. But does everybody get that? Yeah. Mm-hmm. Good with that? Okay. Oh, so a typical Lyons question. If you have liver failure, then technically liver produces albumin. So if you have liver failure, your albumin in your blood would be low. So what would decrease? Oncotic pressure, exactly. So that's a typical Lyons question, you know? So, but if you understand what it means, you can figure it out. You can really, you know, deduce the answer. Same stuff. What's oncotic? What's this? Now, I highlighted that because hydrostatic pressure, which is the P, and oncotic pressure. So Bowman space, hydrostatic, and glomerular, whatever, capillary, oncotic pressure are normally constant. The key word there is normally. It's not accounting for disease or manipulation of other physiological factors. So don't assume that just because you read that, oh, that's never gonna change. It'll change if he asks a question about liver failure, for example. It will change. So, you know, people say, oh, but in the PowerPoint it remains constant. It doesn't, not if you manipulate other factors, all right?
He has like a eye clicker about, he like manipulated something, one of those pressures. I don't know if you remember it.
When you take a picture of the,
I took a picture of all of them. I think that had to do with the half-life of the drug. Was that the
That
same
was
one?
the fifth one.
That was the fifth one?
the one where the pressures go up and down.
I mean, they have it.
Is that the one you're talking about, with the pressures?
Yeah,
Mhm.
yeah. He said it was like, does it decrease?
It was like which one would decrease GFR?
Which one will decrease GFR?
The GFR is not constant, primarily changing due to variation in.
Say again?
GFR is not constant, primarily changing due to variations in.
Isn't it hydrostatic pressure?
But it depends which hydrostatic pressure. Bowman space or glomerular capillary.
You only have those two there?
You had those two, then you also had the oncotic pressures. You like all of it.
I would think it's hydrostatic.
I don't remember the exact question.
That's the
Is that my question? Yeah.
So what is that question?
So the question is, glomerular filtration rate is not constant due to primarily due to a change in what? So when you're looking, this slide answers that question pretty much. So normally, he didn't talk about disease, he didn't talk about anything there. So normally, your hydrostatic Bowman space and your oncotic glomerular capillaries are constant. And the oncotic for the Bowman space is negligible. So obviously your hydrostatic for your glomerular capillaries will be the one that affects GFR under normal conditions, right? If he throws in a disease and he changes things, then if you understand these pressures, it'll help you out. And I'll go more into it because this slide, this PowerPoint goes more into it. Okay, so GFR regulated by ANS, whatever, blah, blah, blah. That's not the important part. That's just memorization. Now, when you decrease glomerular filtration rate, so let's define glomerular filtration rate. What exactly is that?
The rate at which you're filtrating.
Correct. Through the glomerulus,
Yeah.
right? So when you decrease the filtration rate, you decrease renal blood flow, right? That's what the RBF stands for. If you increase glomerular filtration rate, you're still decreasing renal blood flow. Why? The PowerPoint doesn't answer that, but I'm gonna. Right, but I'm gonna answer it for you. So basically, what there's, so first you need to know that renal blood flow and renal plasma flow are not the same thing. They're related and they're proportional to each other, but they're not the same thing, right? Renal plasma flow refers to how much plasma is going through. Now, if you remember hematocrite's about 37 to 45%, so about 55% plasma. Here in the PowerPoint, he goes 600 milliliters plasma, 1,200 milliliters, blood. So it relates, So what happens is that you're looking, the top part talks about renal blood flow, and these bottom graphs talk about renal plasma flow. So that's why this PowerPoint can be a little misleading. So here we're talking about afferent and efferent vasoconstriction. So if we have afferent vasoconstriction, then just think about it like a highway. If I constrict the afferent, then a lot of these cars, aka solutes and ions and stuff, they can't get into the glomerulus fast enough, right? So you decrease naturally your filtration rate. If I don't have anything to filtrate as a glomerulus, then my rate's gonna go down, obviously, because you're constricting the afferent, right? So if you're constricting the afferent, you're limiting the amount of income to the glomerulus, then clearly the hydrostatic pressure in the glomerulus is gonna come down naturally, because you're not getting that much stuff in there. So if that goes down, then the renal blood flow goes down, obviously, the flow of all the stuff getting in. Well, now you constrict the efferent. When you constrict the efferent, you're actually causing a jam in the glomerulus. Because now you're narrowing after the glomerulus. So now things are backed up in the glomerulus. So naturally, if these little ions have more time to hang out in the glomerulus, they're going to filtrate more, thus increasing your filtration rate. But when we look at the bottom graph, you look at the plasma. So on the first side, you see that afferent constriction decreases everything. So hydrostatic pressure is going down, obviously. Renal plasma flow is going down, and GFR is going down. So remember, renal plasma flow and renal blood flow are proportional to each other. Now, in this graph, there's a curveball. So you're still getting decreased amount coming in because you're slowing everything down in general, right? But your hydrostatic pressure in the glomerular capillaries is going up. Why? Because the block is after the glomerular capillaries, so it's building up in there. You understand what I'm saying? So the pressure is obviously going up, and then if the pressure goes up, the filtration rate goes up, because what I said, if the solutes have more time to hang out, then they're going to filter more, but your renal plasma flow is going down. Why? So the renal plasma flow goes down because there's only so much plasma in that backup. So once you start filtering that, yeah, the filtration rate is going up, but you're not getting more plasma in there. So the plasma is going down. Now you can see in this curve, the glomerular filtration rate goes up a little bit, but it is eventually overcome by the fact that there's not enough plasma in there. You see, so the plasma, the fact that that there's not enough plasma to filtrate, it'll eventually go back down. So all you're doing is essentially taking the same amount of plasma and you're filtering more out of it. But when it runs out, it just runs out. And that's why you have that decrease. So if you ask questions about this graph, you know the ins and outs of the graph, you know? Is that clear to everyone?
Yeah.
Okay, all right. This is another one of those memorization things, but basically things like, you know, hypovolemia and stuff, I like to look up definitions so I can understand. Pathology actually teaches you more than lectures ever will. So if you understand why some of these diseases occur and how they affect these organs, then, you know, it actually helps a lot. This is, you know, self-explanatory. The kidney regulates its own blood flow. If you drop GFR, then you drop RBF, you drop, you know, all of that stuff. Okay, again, tubular reabsorption. I put it up there, out, out, out. That means it's going out of the tubules, all right? For some of you that walked in, so understanding these definitions is very important. You know, you have filtration, and then you have reabsorption, and it's tubular reabsorption. And even though the tubule is reabsorbing things, it's not reabsorbing things into it, it's reabsorbing them to go back into the blood. That's very essential, and understand those little differences. And then of course, secretion is the tubules secreting the stuff back in from the blood, and then excretion, exit when you pee.
Is that what he was talking about earlier in the slides, like Vera something? Vasorecta?
Right, so the vasa recta is the capillary that extends down, which extends down with like the tubules, and a lot of that reabsorption secretion occurs. You just look up vasa recta in Google Images, you'll see it. Okay, so, oh, she's not here, okay. I told her something wrong, I gotta correct it. So, this glucose titration curve basically explains how glucose functions in the kidney. But, you know, something that's not really thrown out there, you get this little TM, you know, abbreviation, which nobody knows what the hell it is. And, you know, you're just kind of looking at it like, you know, what the fudge is this, right? So, basically, what it is explaining how glucose moves through the kidneys. So, now that we understand filtration, reabsorption, secretion, and excretion, this makes a lot more sense. So basically what this is saying here is that glucose is reabsorbed by the proximal tubules. Normally, all of the glucose is absorbed, but if you have too much glucose, that was actually an eye clicker question. If you have too much glucose, it can spill into the urine, meaning that if too much glucose is, if you consume too much glucose, then your body is unable to absorb all of it, so it becomes a waste product, right? But why? And this curve explains that. So basically what you have here is you have your excretion rate. So you can see that your filter load is proportional to your excretion rate. In other words, if you filter, you're gonna pee. I mean, that's what happens. So, but then what happens is during reabsorption and secretion, that's all done by transport mechanisms. So what happens is that you can increase the concentration of glucose in the plasma, which will increase the filtration rate of that glucose naturally, but only until you reach what's called the transport maximum. That's what TM means. So the transport maximum means that the channels that are responsible for reabsorbing glucose, they have a limit. You know, you can only saturate them so much before they say, all right, I'm done. And then after that, they shut down, which is what that flat plateau means. And then after that, if you continue to filter, consume and filter and excrete glucose, then you're just gonna spill it into the urine, you're gonna piss it out. That's what that represents. So this tells you that transport channels are responsible for reabsorption and secretion. If you saturate them, they don't work anymore. Is that clear for everyone? Okay. Now this one, it took me forever to figure it out, but you know, it's a little more confusing. But this talks about basically the PAH. My glomerulus is ugly, but it gets the job done. So basically with PAH, what you have is that you're gonna excrete it completely, meaning you're not gonna reabsorb anything. So this is why your filter load and your excretion are opposite from glucose. So you reabsorb glucose, but you don't reabsorb this para-aminohippuric acid. This is why the green line and the orange line are flip-flopped compared to the last one, because you don't reabsorb this stuff. So basically what it's saying, the plateau there kind of throws you off, but it's really not necessary. Think about it like this. You can't secrete something that you never reabsorb. If you don't reabsorb it, if it doesn't reabsorb into the blood, then how are you gonna secrete it back into the tubule? It just doesn't make sense. So if you don't reabsorb it, which is PAH does not get reabsorbed, since it can't be reabsorbed, then none of it is gonna be secreted. So meaning that it's going straight from glomerulus filtration to excretion. And I have another picture that shows that clearly. And this is why PAH is a good indicator of filtration rate, because you're bypassing the reabsorption and secretion mechanism. Is that clear? Okay, no question? All right. I hope I'm making sense here. I don't want to lose you guys.
Keep going.
All right. Okay, so basically what this explains is the formula that if you multiply X is the substance, whatever it is, X can be glucose, X can be whatever. So if you multiply the urine concentration of the substance times the V, which is the flow rate of the urine, that's gonna equal the filtration rate times the plasma concentration of the substance plus reabsorption and secretion. That's basically what that means. All right. Since you know what reabsorption and secretion is, then this all should make a lot of sense. And then the plasma concentration, of course. Moving on. Yes.
And when you say PAH is not secreted, that's what you said? Or
No,
is
no,
it
no.
completely secreted?
No, it's completely.
Oh.
Yeah. So, okay, with PAH, here's the thing with PAH. So, PAH is not reabsorbed, right? But here's what happens: that medically, physiologically, only about 20% of PAH is filtered through the glomerulus, right? None of it is reabsorbed. So if you can't reabsorb it, then technically you can't secrete what you reabsorb. Now, what happens is that the PAH bypasses the glomerulus, the other 80%. So you got 20% that gets filtered. The other 80% continues in the blood flow and is then secreted into the tubule, but it wasn't reabsorbed. You see? So by both mechanisms, filtration 20% and 80% secretion that never got reabsorbed, you have 100% PAH that's leaving. So that's actually a good renal plasma flow indicator, because you're cleaning all of the plasma, you're cleaning the PAH out of all of that plasma through both mechanisms. Follow?
What did TM stand for?
Transport maximum.
I thought it was transport membrane.
No, maximum. It's maximum. Because TM represents the maximum amount of concentration that those channels can hold. Because the channels are responsible for reabsorption and secretion. So the transport maximum represents the maximum load, the maximum concentration of, the maximum rate at which they can reabsorb and secrete. So once you pass that rate, you're overloading the channels, so you're spilling the glucose into the urine through the filtration. It's just getting straight filtered, because it's not being reabsorbed any longer. Is everybody clear on the PAH? Okay. Okay, so GFR, again, just to define it, is the filtrate produced per minute by the glomerulus, right? Normal is between 90 to 120 milliliters a minute. So when you're looking at these equations, I explained these equations, they were on the last slide. But basically, what happens is you don't have to account for secretion and reabsorption. If the substance is neither reabsorbed or secreted, you don't have to account for it. So you simplify your equation to GFR equals the concentration in urine times the flow in urine divided by the plasma concentration of whatever that substance is, substance X. So, that's why you rearrange that equation, because it's not being secreted or reabsorbed. You're bypassing that second mechanism. Again, reabsorbed back into the blood, secreted back into the tubule. Very important. So here we have an example. Again, we saw the normal is between 90 and 120. So here is basically showing you, how to calculate the filtration rate using something that doesn't reabsorb or secrete. So you're taking the urine, you got that number, you got the urine flow, you have that number, and you got the plasma. So you put it together, how the equation says, you get 110. Normal GFR is between 90 and 120, so it's all good. So basically, yeah, she's not here yet. So this means clearance of inulin. He didn't even talk about clearance yet, he's already throwing, abbreviations in there. So that means clearance of inulin, and the clearance, in other words, what you pee out, is equal to the filtration rate if the substance is neither secreted or reabsorbed, because you're just bypassing that mechanism. So that's what that means. And this, this kind of explains that a little bit. So, again, reabsorption and secretion is 0. So you just, whatever's filtered is being excreted. And, that's basically the story. Now, clearance, which is what you pee out, doesn't always equal filtration rate, only in this case. So, don't take that for granted. Now he explains clearance, huh?
Wait, can you say the last sentence you just said?
Oh, that clearance doesn't always equal the filtration rate. So remember, clearance is what you pee out. It's like excretion. But it doesn't always equal the filtration rate. Only if there's no reabsorption or secretion in the tubules, then it equals the filtration rate. Other than that, it doesn't. Important difference. Again, now he talks about clearance. Even though the abbreviation was like 3 slides ago. But basically, the big C means clearance. So C of X is the clearance of whatever substance, X substance. I think that's pretty straightforward. Okay, so in the slide, PAH totally secreted by the kidney. It's kind of a misleading statement. It is secreted, about 80% of it. the main thing here is that it's not reabsorbed. So because it's secreted by the kidney, because it bypasses the glomerulus, and the 20% that was filtered, you get 100% excretion. So whatever you get in, that's what comes out. So it's a good indicator of renal plasma flow, because you're cleaning the entire plasma that was presented to the glomerulus, you're cleaning it out of the PAH. So that's why it's a good indicator of that.
Bless you.
This is the diagram that kind of explains it a little better. So, for example, you look at pH and you look at creatinine. So if you get 100 milligrams in, these numbers aren't physiologically accurate. It's just an example. So you get 100 milligrams in, 20% of it is going to go as filtered. The other 80% is going to continue in the capillary and is going to get secreted. So you get 100% coming out. 100 coming in, 100 coming out. None of it was reabsorbed. So you clean all the plasma that was presented, you cleaned it out of that pH, which is a good indicator of renal plasma flow. Inulin is a good indicator of filtration rate. Why? Because you get 100 milligrams in, you get 20 milligrams out, and you've got no reabsorption and no secretion, and you get 20 milligrams peeing out. So what's coming in is coming out through the filter and not through the second mechanism of reabsorption and secretion. So that's why inulin or mannitol are good indicators of glomerular filtration rate. Does that make sense for everyone? Mm-hmm. Okay. Yeah, what I said. Okay, so the fraction is basically you're taking the GFR and you're dividing it by the renal plasma flow, and it gives you a 20%. 20% is normal. Now, what are things that can jack this up a little bit? For example, if you have renal artery stenosis, right? You're constricting your afferents, remember? So if you constrict your afferents, your GFR is gonna go up because your kidney is gonna wanna compensate. It's gonna wanna filter more with the little bit of blood that it is getting. So actually the top number is gonna go up and you're gonna get an increased fraction. And this is why people take diuretics and things like that. Try to bring that down. That's just a little extra information, but you know, he likes to throw shit like that in there, so.
Wait, can you use that example again? It's so, afferent constriction?
Afferent?
Afferent or deferent?
Afferent. Renal artery is afferent, would be part of the afferent system, because it's coming in. So renal artery stenosis would be decreased blood flow to the kidney, right? So if you're decreasing blood flow to the kidney, then naturally your filtration rate, will go down, but what's gonna happen is your kidney is gonna compensate. This is pathology now. So eventually your kidney will compensate and try to filter more, because it filter more of the little bit that it's getting, you see? Which would increase your fraction from 20% to above normal. And that's the end of that.
Thank you.
So
That's really good.
I'm gonna come early every time. If you guys wanna sit in, you're more than welcome to. If I'm wrong about anything, let me know. I'm a student just like you guys. So, you know, if you see something, if you have more insight, if you see something that doesn't add up, you know, let me know.
Thank you, Tony.
How many people are in that human morph thing on Facebook? If you're not on it, you need to get on it immediately, because Whitney is nice enough to post those questions, the iClicker questions, which are very similar to the test question. Plus, you know, we throw videos up there and stuff that might help you out. So if you're not on that human morph thing, get on it immediately, like right now.